this question is asking us to determine how many solutions the system f of x equals g of x has. So we have two equations here, a quadratic equation and a linear equation. Recall from Algebra 1 that a system of equations can have three different types of solutions. It can have two solutions, one solution, or no solutions. Recall from Algebra 1 graphically that when a graph of a system of equations has no points of intersection, as we can see this graph of f of x and g of x does, that means there are no solutions to this system. So right away, I know that this system has no solutions because the graphs of f of x and g of x never intersect. So right out of the gate, I know that whatever I am going to find algebraically, it needs to support the fact that these graphs never intersect, therefore there are no solutions. So we've dealt with the part of this question that asks us to figure this out graphically, as we see in the aim. Now, how could I figure this out algebraically? So I want to determine whether the solution f of x equals g of x has any solutions. If it's going to have solutions, that means there will be places on the graph where the line and the parabola intersect. In other words, we are going to be having real solutions if these two graphs intersect one another. So what I can do is I can set these equations equal to each other. X squared minus 2 equals negative 2x minus 4. When I combine all of my like terms, I add 2x to both sides. And I add 4 to both sides to get it set equal to 0. I can see that I have a quadratic equation here. Just like we've been doing in the rest of this unit, anytime a quadratic has real solutions or places that the graph would intersect one another, the discriminant will be positive. So I'm going to go ahead and see what the discriminant is for this equation, x squared plus 2x plus 2 equals 0. So I know that a equals 2, a equals 1, b equals 2, and c equals 2. So my discriminant is b squared minus 4ac, 2 squared minus 4 times 1 times 2. And when I simplify this out, I get 4 minus 8, which is negative 4. So since my discriminant is negative, or less than 0, this means there are no real solutions, not only to this quadratic equation, but therefore to this quadratic linear system. We have just reinforced the idea that because the graphs never intersect, there are no real solutions to the quadratic that's formed by setting those equations equal to one another. This leads us to our first key point for today, which is that the solutions of a quadratic linear system are the points where a parabola and a line intersect and can be found algebraically or graphically. Press pause on the video so you can capture this in your notes. So we've dealt with the first part of this question, but now the second part of this question asks us to figure out at least one transformation that would change the number of solutions to the system. So recall from our work on transformations last week that the only transformations that help you change the number of solutions to a system are a vertical translation Remember, that's changing the k value up or down. Or we can use a reflection over the x-axis. So the question that I'm asking myself is, which of these two transformations can I use to make it so that there will be a different number of solutions to the system? So recall from our work in part A that we had no solutions to the system. So now I want to come up with a transformation that will give me at least one solution to the system. So the easier graph to do a transformation on is the linear equation, our equation for g of x. Because f of x is not in vertex form, we could write it in vertex form, but that's going to be a lot more work. So I need to take the graph of g of x and I need to move it. So the easiest way for me to move the graph of g of x is just to move it upwards until it intersects with the graph of f of x. So I can see here, if I translate this line for g of x up by 1 unit, the line of g of x is now going to intersect the equation of f of x at one place. This means that the graph of g of x after a translation of 1 unit up will intersect f of x and create one real solution. If I were to translate it up 2 units instead of 1 unit, make this a dashed line so you can see the difference. We can see one point of intersection here, and if we were to continue this line on, we can actually see that they would eventually intersect a second time up here, giving us our 2 real solutions. So, suggest at least one transformation. I am going to suggest that we translate g of x up by 1 unit, which would make the equation of g of x, rather than g of x being equal to negative 2x minus 4, we are now taking g of x minus 1, which is negative 2x minus 4. I'm sorry, plus 1. We're adding 1. We're adding 1 to the outputs, giving us a new equation of negative 2x minus 3, which matches exactly what we see in this solid black line here, that when we translate our equation up to negative 2x minus 3, we do in fact have one point of intersection. That leads us to our second key point for today, which is that by transforming either the linear or the quadratic function, the number of solutions to the system can change. Please press pause to capture this key point. And finally, we land on our big idea for today, which is that solutions to systems are points where f of x equals g of x. Please press pause and capture this in your notes.